So in this lesson today, we're going to focus on chemistry. So for those of you who are about to learn chemistry or about to take a chemistry course, this video will be very useful for you. So the first thing we need to talk about is the periodic table. Now, I recommend that you go to Google Images and type in periodic table and print one that you could find. But the first thing you need to know are the names of the elements. So on the first column on the left, which is group 1, you have H, which stands for hydrogen, Li, which stands for lithium, Na, which stands for sodium, K is potassium, Rb is rubidium, Cs cesium. Now, it's important to know that the elements in group 1, when they form ions, they tend to form ions with a positive 1 charge. So just keep that in mind. Now, oh, by the way, the metals in this group, like not hydrogen, but lithium, sodium, potassium, rubidium, and cesium, these metals are known as the alkali metals. You need to know that name as well. Now, in group 2, you have elements such as beryllium, Be, and then Mg, which stands for magnesium, and then Ca, calcium, Sr, strontium, Ba, barium. Now, these elements are called the alkaline earth metals, and as an ion, they form a positive 2 charge. The elements in group 1, they have 1 valence electron. The elements in group 2 contain 2 valence electrons. And when they give those 2 valence electrons away, they tend to form ions with a positive 2 charge. Sometimes you'll see it written like this, 2 plus, instead of positive 2. Now, towards the right, we have other elements like boron, aluminum, gallium, indium, thallium, and so forth. So this is group 13, which is also called group 3A in the periodic table. Elements like aluminum, gallium, and indium, they can form positive 3 charges. Next, we have group 4, which contain elements like carbon, silicon, germanium, tin, lead, and so forth. Elements like germanium, tin, and lead, they could form positive 2 and sometimes positive 4 charges. So some ions can have multiple oxidation states or charges. Now, to the right of carbon, you have elements in group 5A or group 15. So these include nitrogen, phosphorus, arsenic, antimony, and bismuth. Nitrogen and phosphorus, they typically like to form negative charges, particularly a negative 3 charge. In group 6A, you have elements like oxygen, sulfur, selenium, Te, tellurium, and then Po. These elements like to form negative 2 charges. They're known as the chalcogens. And then in group 7A, you have the halogens, like fluorine, chlorine, bromine, and iodine. They like to form negative 1 charges. So in group 5A, these elements have 5 valence electrons. In group 6A, these have 6 valence electrons. In group 7A, these elements have 7 valence electrons. The valence electrons are basically the electrons in the outermost energy level, which we'll talk more about that later. Now, in group 8A, you have elements like helium, and then neon, argon, krypton, xenon, and so forth. Helium is above neon, so I didn't really write it. But the noble gases, you need to know that they're chemically inert. They're very stable. So for the most part, they generally do not participate in chemical reactions. So they're highly stable. The halogens are extremely reactive, and so are the alkali metals in group 1A. Now, from group 3 to 12, you have the transition metals. And I'm not going to go through all of them, just a few common ones, such as Ti, that's titanium, Cr is chromium, Mn is manganese, Fe is iron, Co is cobalt, Ni is nickel, Cu is copper, Zn is zinc, and then Ag is silver, Cd is cadmium, Hg is mercury, Au is gold, Pt is platinum, Pd palladium, and those are the most common ones you'll see. Now the inner transition metals, which is below the transition metals, they're called, you have the lanthanide and the actinide series. The most common ones that you'll probably see are thorium, Th, and uranium. The other ones, you'll rarely hear about them in a typical chemistry course. But these two, you might be tested on the names of these elements, so make sure you know those two. I remember on my first day when I was in my AP chemistry class in high school that we were told we're having a pop quiz the next day on naming the elements of the periodic table. And we had like 30 or 40 elements to name. So make sure you know those names because chances are you'll probably have a pop quiz on that. Now the next thing we're going to talk about is distinguishing atoms from molecules. So what is the difference between an atom and a molecule? Some elements are made up of atoms, some are made up of molecules. But what is the difference? Zinc, for example, is a metal that is composed of atoms. Hydrogen, well, not hydrogen, but iron metal is composed of atoms. Carbon is atomic in nature, and so is aluminum. Now, hydrogen is diatomic. It's a molecule. It's an individual particle that contains two atoms. Nitrogen is also a diatomic molecule. It's a molecule that consists of two atoms. So is fluorine, which exists as F2. There's oxygen gas, O2, chlorine gas, Cl2, and then liquid bromine, Br2, and solid iodine, I2. So these are all molecules. Now, you need to distinguish an element versus a compound. A pure element consists of one type of atom, whereas a compound consists of different types of atoms. So for example, zinc is a pure element. It's only composed of zinc atoms. Hydrogen gas is a pure element. It only consists of hydrogen. Sodium chloride is a compound because it consists of two different types of atoms, sodium atoms and chlorine atoms. Iron is a pure element because it consists of only one type of atom, iron metal. Water is a compound because it consists of two different types of atoms, hydrogen atoms and oxygen atoms. And so that's how you could distinguish a compound versus a pure element. Pure elements can consist of atoms or they can consist of molecules. Now, there's two types of compounds that you need to be able to distinguish, and those are ionic compounds and molecular compounds. So, sodium chloride is an ionic compound. Carbon dioxide is a molecular compound. Sodium is a metal. Chlorine is a nonmetal. Carbon is a nonmetal, and oxygen is a nonmetal. So typically, ionic compounds are composed of metals and nonmetals. Molecular compounds are typically made up of nonmetals bonded to each other. But both of these are compounds because they consist of two or more different types of atoms. Metals tend to contain positively charged ions, like cations. Nonmetals tend to form negatively charged ions, also known as anions. So ionic compounds, they consist of ions. Now, the metal-nonmetal rule is, it's not always the case, so to speak. But generally speaking, if you see a compound with a metal and a nonmetal, it's going to be ionic. So some other examples would be like magnesium oxide, that's ionic, or potassium fluoride, that's ionic. However, ammonium chloride is one of those rare exceptions. It's ionic because it consists of ions. However, there's no metal in this compound. Nitrogen, hydrogen, and chlorine are considered nonmetals. And so this is one of those rare exceptions where you have an ionic compound that doesn't consist of a metal and a nonmetal. So at this point, you might be wondering, how can I determine which element is a metal or a nonmetal? And you could use the periodic table to do that. So if you have it with you, you want to pull it out and look for the elements in group 13, starting with boron and then aluminum. And you want to focus on these elements: silicon, germanium, and then arsenic, antimony, Te, and then over here will be like polonium and astatine. And you want to focus on this line that you see here. Some periodic tables will show this line, others will not. So the elements towards the left of this line, they're metals. Metals like to give away electrons, and as we discussed before, they like to form positively charged cations or ions. To the right of that line, you have the nonmetals, which like to acquire electrons and form negatively charged ions or anions. Now on this line, you have metalloids. For instance, boron, for example, is a metalloid. A metalloid has properties in between that of a metal and a nonmetal. So metals, they conduct electricity. Nonmetals do not. They are insulators. Metalloids are in between. They can conduct a small amount of electricity. So the metalloids that you need to be aware of are boron, silicon, germanium. Aluminum is a metal. It conducts electricity very well. Arsenic, antimony, Te. These are metalloids. But on a typical test, the two metalloids that you really need to be familiar with are germanium and silicon. Those are the most common ones that you may have to know or that you'll be tested on. But everything to the left of that are metals, and to the right of that line are nonmetals. And so that's how you can easily tell if an element is a metal or a nonmetal. You need to be familiar with the periodic table. Now, I'm going to give you a mini quiz. I'm going to write out a list of pure substances, and I want you to characterize them as being made up of atoms or molecules, or let's say if they're a pure element or a compound, and if they're a compound, what type of compound? Is it an ionic compound or a molecular compound? So let's start with sulfur trioxide. How would you describe it? So first, is this substance, is it composed of atoms or molecules? Notice that it's made up of many different atoms. So this is a molecule. Now, because it's composed of different atoms, it's not a pure element, but rather it's a compound. So this is called a molecular compound. It's a compound that consists of molecules. Now, what about, let's say, Cl2? Now, this is composed of only one type of atom, so it's a pure element. Now, it consists of molecules, not just atoms, because we have multiple atoms. A molecule can be made up of one type of atom or different atoms. If it's one type of atom, like what we see here, then it's a pure element. But if it's made up of different type of atoms, it's a compound. So this is a molecule. As long as you have basically one unit or one particle that consists of two or more atoms, whether those atoms be of the same type or of a different type, it's a molecule. Now what about, let's say, magnesium? Magnesium is a metal, and metals typically are composed of atoms. And since we only have one type of atom, it's a pure element. And so that's all we can say about magnesium. Now what about sulfur, which typically consists in the form of S8, or it looks like that, S8. Sulfur is actually made up of molecules. So one sulfur unit has basically 8 sulfur atoms connected in an octagonal shape like this. And so that's one whole unit, but it's a molecule because it's composed of multiple atoms. Now, it's not a compound because it's only composed of one type of atom, so this is a pure element. Now, what about this one? LiBr. How would you characterize this substance? So the fact that we have two different types of atoms, lithium and bromine, means that we do not have a pure element. So rather, this is a compound. Now, compounds are composed of atoms or ions. In this case, this compound, it's composed of ions. Lithium is a metal, which is found on the left side of the periodic table. Bromine is a nonmetal, and that's found on the right side of the periodic table. As we know, lithium forms positively charged ions. Bromine forms negatively charged ions. And so we have an ionic compound. So this compound is not composed of atoms, it's composed of ions. Now the video that you're currently watching is the first half of the entire video. So for those of you who want to gain access to the second half of the video, you could find it on my Patreon page if you wish to support it. Now I do have some other video content on that page, so feel free to take a look at that if you're interested in doing so. Now let's get back to this video. Now let's shift our focus to naming compounds. And let's start with molecular compounds because they are a lot easier to name. So let's start with CO2 as an example. Now the first element that we have on the left, which is C, that's carbon. The second element on the right with the symbol O represents oxygen. But the second element will have the suffix "ide." So instead of writing oxygen, we're going to write oxide. However, we do have a subscript next to O, and it's a 2. If you don't see a number, it's always assumed to be a 1. So CO2 is the same as C1O2. Now you need to be familiar with these prefixes. Mono corresponds to 1. Di corresponds to 2. Tri is associated with 3. And then tetra is equivalent to 4. Penta represents 5. And then hexa is equal to 6. Hepta represents 7. Octa is equal to 8. Nona is 9. And deca is equal to 10. Now, we don't have to say monocarbon. If there is a 1 or no number at all, you can disregard the word mono. For everything else, you do have to use the prefix. Now, this is true only for the first element. For the second element, you do have to use the prefix mono. Now, we do have di because of the 2, So instead of saying carbon oxide, we're going to say carbon dioxide. Now let's try these two examples, CO and let's say N2O5. So CO, that's going to be carbon, and this time we have a 1 in front of the oxygen, but carbon monoxide. So for the second element, if there's a 1, you do use the prefix. Now what about N2O5? How can we name that particular molecular compound? So we know that 2 corresponds to di, and 5 is penta. N is the chemical symbol for nitrogen, and O is for oxygen. So instead of saying nitrogen, we're going to say dinitrogen. And instead of saying pentaoxide, we're going to take off the A and use the O. So we're going to say pentoxide. You don't want to put two vowels together. Now go ahead and try these two. SCl6 and PBr3. Take a minute and work on those examples. So S is the chemical symbol for sulfur. Cl is the chemical symbol for chlorine. Now there's 6 chlorine atoms in this molecular compound, and 6 is associated with the prefix hexa. So this is going to be sulfur hexachloride. Make sure to add the suffix IDE. Now what about PBr? So P is the symbol for phosphorus. Br is the symbol for bromine, but we're going to say bromide. And we have a subscript of 3. So 3 is associated with tri. So this is phosphorus tribromide. At this point, let's talk about how to name ionic compounds. So let's start with Ki. How can we name this compound? K is the chemical symbol for potassium. I is the symbol for iodine. But when naming compounds, instead of writing iodine or iodine, we are going to take this off and replace it with ide. So it's going to be iodide. And that's the name of this compound, potassium iodide. That's all you need to do. Now what about MgBr2? Keep in mind, the rules for naming ionic compounds differ from naming molecular compounds. Mg stands for magnesium. Br is bromine, but we're going to add the suffix ide. So the answer is magnesium bromide. For ionic compounds, you do not use the prefixes mono, di, tri, tetra, and so forth. So there's no need to call this magnesium dibromide. Magnesium bromide will always be MgBr2. Now go ahead and try these two examples. Write the names of these two ionic compounds. So the first one, Ca, stands for calcium, and O is oxygen, but we're going to add the suffix ide. So the answer is calcium oxide. For the next one, Sr stands for strontium, and F stands for fluorine, but we're going to write fluoride instead. So this is strontium fluoride. Now as you can see, naming ionic compounds is not too difficult. Now you need to be familiar with something called polyatomic ions. Poly means many. So these are ions that consist of multiple atoms. So some common polyatomic ions would be SO42-, which is called sulfate, OH-, that's hydroxide, NH4+, ammonium, C2H3O2-, that's acetate, let's see, NO3 minus, that's nitrate, PO4 3 minus, phosphate, CN minus, cyanide, MnO4 minus, permanganate, Cr2O7 2 minus, that's dichromate. And there are some other ones, but I have a video on polyatomic ions on YouTube. You can feel free to check that out if you want a more detailed list. Now, I recommend memorizing the list that you see here because you're going to see these ions, you're going to use them a lot in the rest of your chemistry course. So make sure to commit that to memory. So let's say if we have the ionic compound Na2SO4, how can we name it? Well, using the periodic table, which you'll typically have access to on an exam, you can see that Na is sodium. Now, SO4, that is not on the periodic table. You need to recognize that this is a polyatomic ion. So once you know it's sulfate, all you have to say is sodium sulfate. And that's why it's important to commit these to memory. So for example, let's say if we want to write the name of KNO3. K stands for potassium, and you simply need to know that NO3 represents nitrate. So this is called potassium nitrate. Go ahead and try these two examples. AlOH3, and let's say LiC2H3O2. So Al stands for aluminum, and OH is a polyatomic ion known as hydroxide. So this is simply called aluminum hydroxide. Now for the next one, we know that Li represents lithium, and C2H3O2 is another polyatomic ion that you need to memorize, and that's called acetate. So this is lithium acetate. Now, how would you name these two? FeCl2 and FeCl3. Be careful with these two examples. Now, Fe we know is the chemical symbol for iron, and Cl is chlorine, so we could say it's chloride. And so this is going to be called iron chloride. Now, that would be correct, but there's more to it. Now, these are actually two different ionic compounds, and we can't use the prefix di and tri. So we can't use iron chloride to identify these two different substances. We need to do something else. Now, typically, when you have a transition metal or some other non-transition metals that have multiple oxidation states or multiple charges like this element, iron, you need to use Roman numerals. The first thing we need to do is determine the oxidation state or the charge on iron metal. So let's focus on FeCl2. So we have one Fe particle and two chlorine particles. What is the charge on chlorine? Chlorine likes to form a -1 charge. So the total negative charges are -2. Now there's one Fe particle, and so it has to have a +2 charge in order to neutralize the net -2 charge rather. And so to name this, it's going to be iron 2 chloride because the oxidation state of iron metal is +2 in this particular compound. So at this point, you can guess what the name of FeCl3 is going to be. So we have 3 chloride ions, which means the total negative charge is -3. So this Fe atom has to have a total +3 charge. And so since the oxidation state of iron metal is +3, this is going to be called iron 3 chloride. Now for those of you who need to review Roman numerals, I do have a video on that. So if you were to type in Roman numerals organic chemistry tutor in YouTube, it should come up if you need to review Roman numerals. Go ahead and try these two examples, PbO and PbO2. So let's start with PbO. Pb represents lead. O is oxygen, but we're going to write that as oxide. Now we need to determine the charge on lead. We know the charge on oxygen is -2, and so the charge on lead is +2. So these numbers have to add up to 0. We only have one oxygen ion and one lead ion. So because we have one of each, the charges have to have the same magnitude, but the opposite sign. So now that we have the oxidation state of lead, we can write the name. So this is called lead 2 oxide, since it has a +2 charge. Now, there's something I do want to mention. When writing ions, some teachers will want you to write the ion this way as opposed to this way. So they may want you to write Pb2+ instead of +2. And even in certain online homework assignments, you may have to input it this way. Me, technically, I have the habit of writing ions like this. Sometimes you may see me write it this way too, but in case I just naturally revert back to my old habits, just keep in mind that you may have to write it this way if your teacher requires you to do so. So I just want to put that out there. Now let's go back to this one, PbO2. So what is the oxidation state of Pb in this example? A simple way to find the answer is to write an equation. So we have one Pb atom and two oxygen atoms. I'm going to write as OX so that you don't distinguish, so you don't think of O as 0. Now, the net charge of this compound is 0, so we're going to set it equal to 0. Our goal is to solve for Pb. Now, we know the charge on oxygen is -2. So 2 times -2 is -4. And if you add 4 to both sides, you'll see that the oxidation state of Pb is 4. Or if you do it the other way, so we have one Pb ion and two oxygen ions, each with a -2 charge. So the total negative charge is -4, which means the total positive charge has to be +4. And so we have lead 4 oxide. Now what about this one, Cu2SO4? How can we name that particular ionic compound? Go ahead and try that. So let's write an equation. So we have 2 copper atoms. Now SO4, you don't want to split that into separate atoms. Instead, recognize it as one unit. It's a polyatomic ion. And the net charge has to be 0. Now we know the charge on the sulfate ion, which is -2. And so if we add 2 to both sides, we'll get 2Cu is equal to +2. And now let's divide both sides by 2. 2 divided by 2 is 1. So the oxidation state on copper is +1. Now let's confirm it with the other technique. In this case, we have 2 copper ions and 1 sulfate ion. The charge on sulfate is -2. So that's the total negative charge. The total positive charge has to be +2. And when you divide that to the 2 copper atoms that we have here, each of them has to have a +1 charge. So that is the oxidation state of copper, +1. So this is going to be called copper 1 sulfate. Now let's talk about writing formulas of compounds. So let's start with molecular compounds. Let's say if I give you the name, we'll go with phosphorus pentachloride. What is the chemical formula of this molecular compound? Now, to write the formulas of molecular compounds is pretty straightforward. It's simply the reverse of what we've been doing before. Phosphorus is P, and then we have chloride, so Cl, and penta tells us that we have 5 chlorine atoms. So the answer is PCl5. Now let's try a few other examples. So what about sulfur tetrafluoride. Try that one. Sulfur is S, and then we have fluorine, and tetra tells us that we have 4 fluorine atoms. And so that's it for this example. Now let's try one more. Nitrogen monoxide. So we have nitrogen, and mono means one, so we have only one oxygen, and so NO is nitrogen monoxide. Now, writing formulas for ionic compounds could be a little bit more challenging. So let's start with something simple. Let's say potassium bromide. Now, if you were to say it's KBr, you would be correct. Now, what about this one? Let's say if we have sodium. Actually, let me use something different. Let's say aluminum sulfate. How would you write the formula for that ionic compound? Now you might be thinking aluminum is Al, sulfate is SO4, so AlSO4. If you do it this way, the answer will not be correct. You need to make sure the charges of the ions are balanced. Aluminum has a positive 3 charge, or you could write 3 plus if you want. Sulfate has a negative 2 charge, or 2 minus charge. Now what we need is, in order to make the total charges the same, we need 2 aluminum ions, which will give us a net charge of positive 6, and 3 sulfate ions, which will give us a net charge of negative 6, and these 2 will cancel. So it turns out that the formula is Al2SO4 3. Now whenever you have multiple polyatomic ions, you need to enclose them within a parentheses. Now let's try some other examples. So let's say if we have potassium phosphate. What is the chemical formula for this compound? So start by writing the ions. Potassium has a positive 1 charge. Phosphate has a negative 3 charge. Now a quick and simple method is to replace the numerical value of the charges with subscripts. So this is going to be K3PO4 times 1, which we could simply leave it as PO4. And using that technique, you can quickly write the formula for the ionic compound. So it's K3PO4. Try this one. Calcium iodide. Feel free to pause the video. Now, calcium is an alkaline earth metal. It's found in group 2, so it's going to have a positive 2 charge. Iodide is a halogen in group 7A, and those elements form negative 1 charges. So if we switch the charges with subscripts, it's going to be Ca1I2, but we don't need to write the 1, so it's simply CaI2, and that's the answer for that example. Now what if we have iron 2 sulfide? Not sulfate, but sulfide. Sulfate is SO4 2 minus. Sulfide is different. So what if we have this? How can we write the formula? If you see the Roman numeral, it tells you the charge or the oxidation state on Fe, which in this case is 2 plus. Sulfide is simply sulfur, which is a chalcogen in group 6A, and those elements typically form a negative 2 charge as an ion. Now, anytime you have 2 ions with the same charge, you could simply write them together, so the answer will be FeS. If you use this technique, you're going to get Fe2S2. Now, if you have even numbers, you can reduce it. So you can divide the subscripts by 2, and that will give you Fe1S1, which is basically FeS. So anytime the charges are the same, you could just simply write them together as FeS. Now let's try this one. Aluminum, phosphate. So go ahead and take a minute and try that example. So aluminum has a positive 3 or a 3 plus charge. Phosphate is PO4 with a 3 minus charge. Now, because the charges are the same, we can simply write them together. So the answer is going to be AlPO4. And that's it for this example. Now, what about copper to phosphate? What about this example? So we have copper, and the Roman numeral 2 gives us its oxidation state. And phosphate is still the same, PO4, 3 minus. Now this time, let's swap the charges and write them as subscripts. So it's going to be Cu3 and then PO4. So we need to write this within a set of parentheses. And then let's write the 2 as a subscript. So this is going to be the answer. So anytime you have multiple polyatomic ions, you need to write it within a set of parentheses. Try this one. Tin 4 oxide. Tin is represented by the chemical symbol Sn, and we have a 4 plus charge. Oxide, it's going to be O2 minus. Now the charges are different, so if we swap them and write them as subscripts, it's going to be Sn2O4. Now notice that even though the subscripts are not the same, they're both even. In a situation like this, you want to reduce it. So divide each subscript by 2. So it's going to be Sn1O2, but we don't need to write the 1. So the final answer is going to be SnO2. So that's the chemical formula of tin 4 oxide. Now here's the last one. We're going to try vanadium 5. Let me do that again. Vanadium 5 oxide. So vanadium has the chemical symbol V, and it's going to have a positive 5 charge, or 5 plus charge. Oxide will have a negative 2 charge, and if we switch them, it's going to be V2O5. And so now you know how to write the chemical formula of ionic compounds. So now let's move on to our next topic. Now, if you have access to a periodic table, look for the chemical symbol N. It has an atomic number of 7 and an average atomic mass of 14.01. Sometimes this is referred to as the mass number when dealing with isotopes, but on a periodic table, it is known as the average atomic mass because there are many isotopes of nitrogen. And this is the atomic number. But let's talk about isotopes, and we'll get back to average atomic mass. Now let's focus on the isotopes of carbon. That is carbon-12 and carbon-13. These are the most common isotopes of carbon. There are some other ones, but carbon-14 is another version. But let's focus on just these two. So these two isotopes, they share the same chemical reactivity. They're essentially the same. They are both atoms of carbon. So in a chemical reaction, they will behave the same way. However, they do have different nuclear properties because the structure or the makeup of their nucleus is different. Now, when you look at carbon on a periodic table, it's going to look like this. You're going to see the atomic number of 6, which is true for all isotopes of carbon. And you'll see the average atomic mass. So this mass is the average of all the masses of the isotopes of carbon, including carbon-12, carbon-13, and carbon-14. Now here's a question for you. Which of these 3 isotopes is the most abundant isotope of carbon on Earth today? Well, because the average atomic mass is closest to 12, carbon-12 is the most abundant isotope. But now let's talk about it. Let's calculate the number of protons, electrons, and neutrons in these two atoms. To calculate the number of protons, it's always equal to the atomic number. To calculate the number of neutrons, which is found in the nucleus, it's the difference between the mass number and the atomic number. Now, the number of electrons is equal to the atomic number, which is basically the number of protons, minus the charge. So atoms are electrically neutral. They have no charge. So for atoms, the number of electrons and protons are the same. For ions, they have a charge. So in the case of an ion, the number of protons and electrons differ. A positively charged ion has more protons than electrons. A negatively charged ion has more electrons than protons. Protons are positively charged, electrons are negatively charged, and neutrons are neutral. So in the case of carbon-12, which I'm going to write this like this, it has a mass number of 12 and an atomic number of 6. This is the opposite in which you see it in the periodic table. So carbon-12 has 6 protons because that's the atomic number. The number of neutrons is the difference between 12 and 6. So that's going to be 6 neutrons. And for an atom of carbon, it's going to be 6 electrons. Now for carbon-13, sometimes you'll see it written this way. So this is the atomic number, and this is the mass number. Carbon-13 has 6 protons. And the difference between the mass number and the atomic number, 13 minus 6 is 7. So it has 7 neutrons. And we don't have a charge, so it's still 6 electrons. So the difference between these two isotopes has to do with their mass number. One is 12, one is 13, and the number of neutrons. So make sure you understand that because that's a common test question. Isotopes have the same number of protons and they have the same atomic number, but they differ in the number of neutrons and they have different mass numbers. Now, for the sake of practice, I want you to determine the number of protons, neutrons, and electrons in an atom of nitrogen 15. So this is one of the isotopes of nitrogen. In an ion of aluminum 27. And let's say this ion has a charge of positive 3. And of an ion of, let's say, sulfur 34, which has a charge of 2 minus. So go ahead and calculate the number of protons, neutrons, and electrons. Starting with nitrogen, the number of protons will be the atomic number, which is the smaller of these two numbers, so that's 7. The number of neutrons is the difference between 15 and 7. 15 minus 7 is 8, so we're going to have 8 neutrons. Now, because there's no charge here, this is an atom. And atoms, as we said, are neutral. They have equal number of protons and electrons. So this atom has 7 electrons. Now, in the case of the aluminum cation, keep in mind cations have positive charges. We need to determine the atomic number first. And we could find that in the periodic table. So if you look up aluminum, you'll see that the atomic number is 13, which means that it has 13 protons. Now, if we subtract 27 by 13, that will give us 14 neutrons. Now, we do have a charge, and so the number of electrons will differ from the number of protons. To calculate the number of electrons, it's going to be the atomic number minus the charge. So the atomic number is 13, the charge is positive 3. A negative times a positive is a negative, so this becomes 13 minus 3, and so that gives us 10. And thus we get 10 electrons. And as we said before, whenever you have a positively charged ion, there's going to be more protons than electrons, which we could see that there's 3 more protons than electrons. Now let's move on to the other example. So let's find the atomic number of sulfur using the periodic table. Sulfur has an atomic number of 16, which means that there are 16 protons. Now 34 minus 16 is 18. So this particular isotope of sulfur has 18 neutrons. Some other isotopes of sulfur are sulfur 33 and sulfur 32. The one that we're dealing with is sulfur 34. The mass number identifies the isotope number. The atomic number identifies the element. So anytime the atomic number is 13, you know that the element is aluminum. Anytime the atomic number is 7, the element is nitrogen. So the atomic number identifies the element, and the mass number identifies the isotope within a certain type of element. Now let's calculate the number of electrons. So it's going to be the atomic number 16 minus the charge, which is negative 2. A negative times a negative is a positive. So 16 plus 2 is 18. Notice that we have more electrons than protons because we have a negatively charged ion, which is an anion. So now you know how to calculate the number of electrons, protons, and neutrons.